Okay, so good afternoon, everybody. We're gonna try and see how this works. So bear with me as we work through this. And basically, this is what the overall process is gonna look like. I'm gonna kind of help us walk through this document almost as if we were in class, and then I'll open it up for you all to do some discussions based off of it. So I'm basically going to go through this document, run through the main ideas and formulas. We'll do our calculations on here, and then you'll all have the option to take a look at this whenever you want. And I'm also encourage you as we move through to kind of take account and pause and look at the formulas as we go through them. I'd encourage you to pause and practice with them, and I'll also work with your group mates as we kind of make it through this. So I'll go through this. We'll give this as a sort of dry run, and then hopefully it will get smoother as we move through this. So basically, we're going to be looking at chapter 7 today, and I'll have this document posted for you all to take a look at too. And these are, as always, these notes will always be available on our Canvas site, the regular outline from which I'm taking this off of. But so let's get started on this. So basically today we're going to be looking through the idea of estimation. So when we're taking a look at estimation, our goal really here is to be kind of taking advantage of the different aspects of what we've been talking about so far in the semester, looking at estimation here, and trying to just take advantage of some of the things with the normal curve. So as we've talked about, the most of stats is all based on this normal curve. And if you remember, a lot of these things all have to do with the distribution here. It's this essence of what our stats is based off of. So last week we sort of looked at the idea of what it takes to be to, to take a sample from the normal curve. And today we're going to kind of look more deeply into exactly how precise we were with anything that we did. So as far as this goes, it's all on the same scale as before. And if you recall, if you look at these ones down here, they're all standard deviations. And because it's a predictable amount, we could actually make estimations on this. So, 1, 2, 3 standard deviations, all with a precise amount of percentage that we could guess under the curve. So what we could do with the estimation then is we could start actually making predictions on how likely it is that a sample we've taken falls within this distribution. That's really all we're doing here. So look over here, refers to our ability to make smaller samples and predict the characteristics, the tendencies, and composition of the larger population. So essentially, most research is based off this idea. So we're really just taking a little bit closer look at what all this is about. So to get into this, there's basically two types of estimates, and we're going to be focusing on one for the purposes of our class. So two types of estimates, one being the point estimate, which really is not as good. And a sample of this would be something along the lines of, we're basically saying that a sample is exactly within this. And point estimates might be useful if you are actually just getting started with a project and you wanted to make an overall guess as where things might be going. So point estimates along the lines of, if we were to look back at our, if you to pull up your notes. So I'll pull back up here. These are something you all could have opened up as well. So point estimates are right here. This poll for who identifies as environmentalists. If we just did this poll in our class, for instance, everyone raise their hand who identifies as environmentalists. And maybe we found that 42% of respondents said yes. So that would mean that 42% of this group said yes. And if we were then to make an overall estimate that we could say that the whole population is COD, for instance, was 42%, it's a bit of a limitation because we're saying that our sample exactly mirrors the overall population. If you remember back when we were talking about sample versus interval, or sample versus population, sample is supposed to be a representation of the larger whole. So when we talked about sample before, it was the idea of we estimate that this amount can represent a bigger group. So when we said like satisfaction survey for COD, we asked maybe our class, and then we could estimate that those 30 students from our class represent the overall satisfaction of COD. But if we just took that exact number and said this is it, then we're probably not going to get it we're not going to likely not to get it exactly right, because the exact value isn't going to be the same. However, with the way we might control for this, and we've probably seen something like this, is going to be something like interval estimates. This one here. So interval estimates have a range of what we might expect. So for example, in elections, we might hear something like the candidate is at 83% of people say they're going to vote for this candidate, and you always see something like plus or minus 3%. And that really is just, that's the range. The plus or minus 3% is, it could be 86%, it could be 80%, but we're pretty sure, and we'll get into exactly how sure we are, that it's within that interval. And this is where we talk about the interval estimate, because we're giving a little bit more leeway in how we're thinking about things, and also acknowledging the fact that even though it does fall along the normal curve, that there's a range within, we might not actually have the actual numbers. And just going back again, the reason we choose samples over doing the whole population, because generally we don't have the means to do a full note of everybody in a population. So we have to do a sample of it. We don't have the means financially, or maybe time-wise. So the so what part of all this, right? So the whole idea of this is we want to be able to have a confidence interval, so we start predicting the chances that we got it right. So the key term here is confidence interval, or the chances that we got it right. And there's a formula over here to the right, and we'll be referring to this throughout. This formula right here. The confidence interval, CI, is basically going to equal, and I'll read through this, and we'll actually do a few samples below, is the mean or average of the group, plus or minus, and I'm going to double underline this because this is going to be important later on, the z-score times the standard error. So we'll break this equation down, but essentially you're going to be plugging in something to two different equations, and it'll give us a range. It'll give us the actual numbers. It'll be this plus or minus stuff here. Okay. So the typical estimates we have is 90%, 92%, 95%, and 99%. And these all match the amount of error that we might expect from that. So if you're 90% sure, it's going to be 10% error. For 92% sure, 8%, 95% sure, 5% error, and 99% only 1% error, respectively. And the reason we're thinking about this, it kind of goes back to our ztable.com idea. So if you were going to pause it, if you want to open this website up again, it's our nice little z-score table that we were using last week. The z-score table. If you remember these things. And it's basically referring to some of the questions we had done last time, where something like when we say 90%, we want to look in here and find something in this area here where it looks closest to 90%. So here, remember from before, it was this 0.8997, right? And that's 1.28, about 90%, because 8.8997 is closer to 0.9 than 0.915 is, right? So that's the way we'd end up saying that the z-score of 1.28 is at 90%. And these percentages, like I'm saying, are all corresponding to these. So the z-score for 90% would be 1.28, and so on and so forth, right? So z here is always referring to the z-score. And if you would scroll down a bit, I have a bit of some samples here. These are the common ones, and they all refer to the confidence interval and the corresponding z-score. And it's a little off here, but you can see that 80% is 1.28 z-score, 90% 1.64, 98% 2.33. So these are the scores you would use when you're looking that up in the any questions you have for the homework. Go ahead and just use these scores here. So having reference to that table would always be useful, or you could always go in and look at the actual Z table and pick it up as well. Okay, so example. I hope you you'll enjoy the rainbow font there. Basically, most of the questions for the homework are going to look something like this. They're going to be a different version of this sort of problem right here. So I'll read through the problem and we'll read through the steps, and then we'll go over to this side where they're actually going to have the step-by-step ways of doing it. So like we do in class, I'm going to read through it. We'll see how to plug in all these numbers and have all the relevant things plugged in or underlined, and then we'll go through it. And I would encourage you to as well, to pause and actually run through these numbers yourself so you get familiar with entering them into a calculator. But we'll also do it live here. So step one, as we go through this, is calculating the standard error. And all these are going to be from the problem here. So I'll go ahead and read the problem. So the problem where we're trying to determine how to address the needs of 15,000 commuter students with a sample size of 500 students. Sample size is relevant here, something to pay attention to. We are looking at an average commuting time per week. In our sample, we find that the average time is 7.5 hours commute time per week with a standard deviation of 1.5 hours. So the question is, how would we determine a 95% confidence interval? Basically asking, how likely is it that we got it right with 95% confidence that we got it within this range? Okay, so we're going to go ahead and do step one, and I'll show you what that looks like. And again, I'll go through the different steps, and then we'll look at how to plug it into the equation. And of course, pause if you need to. So step one, calculate the standard error. So it's a really simple formula. It's just right here. So this little symbol here that I'm going to circle, that is the symbol for standard error. Okay? It's a symbol for standard error. So that one's important because that's what we're going to be plugging into the second part. So essentially you have two equations that you need to do this one first and then do the other one second. So a calculated standard error is simply finding the standard deviation, which is always going to be up here in the question. And then n as before, n is always the sample size. Okay, so sample size of students. And don't forget that it's under a square root. So it's the square root of the sample size. So overall, this is standard deviation up on top. And on the bottom, it's the square root of the sample size. So recall that this is sample size and that's not the total number of people. Okay. Step two, deciding the level of confidence, the z value. So step two, the 90% in this case is what we asked for, or we asked for 95% in this level. So in this case, you'd go back up to our little z table and look at 95%, and then you're going to plug in the 1.96. Okay. So now we go through and actually start plugging these things in. So we're going to look over here to the right, and here's step one. Got to calculate the standard error. So that's from the first equation. So standard error is standard deviation divided by square root of the sample size. In this case, the 1.5, which we've got over here, divided by the square root of 500. And again, you want to make sure you're looking at the number of students and the sample size, not the total. Okay, so we end up getting this number here, 0.067, or rounded up for the purposes of this equation, 0.07. Okay, so now we plug it into the formula, and the formula we're referring to is this one up here. So if you look at this one, the formula equals y, or the mean, plus or minus z times the standard error. So we just calculated this one, so we could plug that one in. We have the z-score, because we know it's 95% confidence interval, and y is the average. In this case, it's going to be a 7.5. So we're going to go back through and just plug them in. And here's what I'm going to emphasize again, the plus or minus part. So you're basically going to be doing two equations with this. So you have the first one you do, and the step two requires you to break it into two equations. So I have here a note, do both equations. Don't just do one of them. So the plus or minus splits it off into two. And I'll show you what I mean. So for the plus version of it, you take the 7.5, which if you look above, this is the mean, which is over here, 7.5 hours. So we're plugging that in so it'll stay the same. 7.5 plus, we got the 1.96, because that's the z-score over here at 95%, 1.96. Let's go ahead and plug that in, 1.96 times 0.07. And the 0.07 is just the standard error you got from the first part. So essentially at this part, you're just plugging in the information, right? So 7.5 plus 1.96 times 0.07, and also 7.5 minus, there's where the plus and minus comes in, 1.96 times 0.07. Going down here, this is the simplified version of it. You do the parentheses first, so 7.5 plus 0.1372 and 7.5 minus 0.1372. So basically what you end up doing is you end up getting the range from this. So when you do 7.5 plus 0.1372, you end up down here at the 7.6372. That's the upper range. Pardon the penmanship there. That's the upper range. And then you do the second equation, the 7.5 minus 0.1372, and that gives you the lower range, which we'll type it in this time. So just make sure you pay attention to which one's upper, and in some ways it's easy because upper is just the higher number and lower. So basically then when you start saying the confidence interval is what we end up saying. Our confidence interval is we're 95% sure that our sample that we did, our sample of 500 students, is correct in saying that the average commute time is somewhere between 7.3628 and 7.6372. So just remember when you're actually putting it, and I noted it, but when you're actually putting this in your homework, just note that you make sure you put them in the proper spot. So this is the upper number, 7.6372, and this is the lower bound, 7.3628, okay? So make sure you have those separate. So if you want to pause it here and rewind it, take a look at it, but basically that's it for this part. And if we were to do a second one, we'll run through the second one on this. So it's going to be a similar idea, let's plug them in differently, so you could go ahead and get more practice with this, and it's worked out over here to the right. So the same problem, where we are trying to determine the address and needs of 15,000 computer students, so that's the population size, with a sample size of 300 students, so 300 students is a sample. And we're looking for the average commuting time per week. So we find our sample, we find the average time is 9.5 hours, so there's our average. With a standard deviation of 2.5, how would we determine a 90% confidence interval? So again, same numbers you're plugging in, you're just going to plug them into their corresponding spots. If you look over here, again, first step, step one, is always going to be standard error, which from above is the standard deviation divided by the square root of the sample size. So you're just going to go back and look at your numbers. We got 2.5 here. So right here, 2.5 hours is the standard deviation. And you divide that by the square root of 300. 300 again, sample size, not population size. So 300 students over here. And make sure it's the square root, because if you recall up here, it's a square root of the number in the sample, not just any old square root. Okay. You end up with 0.067. I'm sorry, that's from the previous number. This actually should be, well, let's go ahead and do that. So you do square root 2.5, I'm doing this on my own calculator, 2.5 divided by 300 square root equals, yeah, this should actually be 0.1443, and we're gonna go ahead and round that over to 0.14 for the purposes of this problem, because we're rounding up from here. So step two, we're plugging into the formula. So we go ahead and take the number we just got, the standard error, and we're plugging it in down here. And this is just in reference to this, the main formula we'll be using up here. Standard error is this one. This is the one we're plugging in, and this one we just calculated, 0.14. And we're taking 1.64. That's the z number in this case. So if you go over here, we got the confidence interval for the second one of 90% confidence. So you can go ahead and look up above 90% confidence interval of 1.64. And these numbers here are all reproduced in the notes that I have posted on campus. But of course, you could also use this. So plugging in the 1.64 down here from the z-score. And the 9.5 is just the average. So if we're looking back at our formula again, the average, and that is right from the problem itself, the average time is 9.5 hours. So we plug that one in. So it's 9.5 plus or minus 1.64 times 0.14. And again, note to do both equations. You want to do the plus version and the minus version. So same thing here. I just wrote it out by plugging in the numbers. And then we're going to do the math to get rid of the parentheses. And that's going to give us 0.2296 for both of them. But one version, of course, is plus. One version is minus. So if we plug those in, we get the upper version. And again, upper is 9.7296. And the lower version is 0.92704. So essentially then you got your range, and again this is always keep track, this is lower and this is upper when you're plugging this into the homework, because Canvas isn't asked specifically for upper and lower, and make sure you put the numbers in correctly. So I guess just as far as tips go with this one, always make sure you keep track of your steps. First step is always going to be calculating the standard error. So you can plug into the second equation. And the second equation is this one up here. And just making sure you keep track of the plus and minus. So splitting that step 2 into 2 parts. And it should give you relative ease as far as plugging these in, because the homeworks look very similar to this. And just things to keep in mind. There's a chart here, and again, this is in your book if you have the book, and it's also in our notes, this actual screenshot. So you could pause it here and take a look. But essentially what this is doing is it's a sort of logical way of looking at what we do with confidence intervals. So this whole thing is how sure we are we got it right. So logically, if you manipulate some of the sample sizes or your confidence interval, it's going to affect on how precise you are. And what I mean by that is, for instance, if the sample size goes up, right here, if the sample size goes up, the confidence level becomes more precise, meaning you're more sure that you got it right. And that's because, remember, as the sample size gets closer to the actual number, the more precise you're going to be. So for instance, if you ask 30 students, and this is supposed to represent, you know, College of the Desert, everyone at College of the Desert's satisfaction with the school, and you say, ask 30 students, it's not going to be as accurate as if you ask 200 students. Just the more students you ask, the closer you get to the actual number, the more precise you're going to be. So in this case, if the sample size goes up, confidence interval becomes more precise, right? Similarly, if the confidence interval goes down, so if you're not, it's basically saying, if you're not as sure about you got it right, if I'm 99% sure and I drop down to 95% sure, the confidence interval becomes less precise because you're not as sure you got it correct. Similarly, sample size goes down, which is opposite of the other one. Sample size goes up. You're less confident that you got it right. So your step is less precise, right? Okay. So if the value of the sample standard deviation goes up, this is another version of this. And this has to do with you plugging these numbers into your equation. So that number you plug in, and we'll go back up here. That number you go in, and this error, the standard deviation right here, as that one goes up, the confidence interval becomes more precise, because again, this is dealing with how much of that normal curve you're encompassing. So wherever up here, standard deviations are always referring back to our normal curve. So the bigger your standard deviation is, the more of the curve you're encompassing, the more of the curve you have covered. Therefore, the more accurate it's going to be. Okay. So following along here, similarly then, if the opposite is true, if the standard deviation goes down, you're covering less of that normal curve. You become less precise. Okay. And again, if the confidence interval goes up, for if you're 95% sure to 99% sure, the confidence interval becomes more precise. Okay, so it's just a matter of following these things. There's a few questions that refer to this chart, and it's basically just noting your concepts for here. Okay, so basically, just as a quick recap, I would just be a few things to look out for that come up on the homework is, well, for one, making sure your lower and upper bounds are put in the correct spot on the homework. So make sure you get that. Make sure you do both equations, pluses and minuses. And just follow the steps, so always do this one first, the standard error, and then always just plug it right back into the formula. Okay, so as we go through this. And just a note on SPSS work. So for now, as we're trying to navigate not having access to the online classes, I'm going to hold off on any SPSS problems. So if you see one on the homework, I have marked it as 0 points. So it's not going to count anything, right or wrong. And if this goes on, our access to SPSS, if this closure goes on for much longer, then we'll figure out a way to work around this. And I think there's free samples and free trials of the SPSS program, and we'll deal with that as we move on. But for the purposes of what we're doing so far, go ahead and you could skip it, or you could just fill in whatever numbers you want, because we're 0 points for right now. And as we get further along in the semester, we'll have to start working through that. But for the purposes of this first homework that we're doing remotely, go ahead and just don't worry about it. So go ahead and get started on the homework, and we'll give you all a week to work on that. And also just try to get in with your groups and do group projects, and try to schedule a time where y'all could sit down and try to do this remotely so we could try to retain as much of that collaboration as possible.